All right, this lecture is on stoichiometry. Stoichiometry is one of the most important concepts for chemists. It allows us to predict how much product will be formed given a certain amount of reactant, or how much reactant is required to make a certain amount of product. And it's really no different than if you're at home and you have a recipe that says that you need 2 slices of bread and plus 1 slice of meat to make a sandwich. And let's say you've got 4 slices of bread on hand, but you only have 1 slice of meat. How many sandwiches can you make? Well, this is the limiting reactant, right? This is the limiting substance that determines how many sandwiches. So even though you've got enough bread to make 2 sandwiches, you only have enough meat to make 1 sandwich. So this would be similar. The recipe is similar to what we call a balanced chemical equation in chemistry. These numbers out in front are called coefficients, and they tell us the relationship between substances. So for a chemist, we have something like this. Let's say I want to react methane with oxygen. And anytime you burn a hydrocarbon, a carbon-hydrogen compound, and oxygen, you will always get carbon dioxide and water as your products. All right. So the first thing we have to do is balance this chemical equation. That's just like the recipe up there. This really doesn't mean a lot until we make sure that it's balanced. So going back to one of the principles of chemistry is matter cannot be created or destroyed by a chemical reaction. So all atoms have to be accounted for on both sides of the chemical yield sign. So we look at this. We have 1 carbon on both sides. We have 4 hydrogens on the reactant side here. We only have 2 hydrogens here. Now we can't just erase the 2 and put a 4 there, because that wouldn't be water anymore. It'd be something else. So all we can do is put a 2 here in front of the water. That's called a coefficient. So now we have 4 hydrogens on both sides. And the last thing we want to balance is the oxygen. So we've got 2 oxygen here plus 2 times 1 here. So we got a total of 4 oxygen, so I need a 2 in front of the oxygen there. All right, so our equation's balanced. So that's our recipe, that's our equation. Let's say someone said we had 10 grams of methane and an excess amount of oxygen. That means we got plenty of oxygen for the methane to react. And the question is, how many grams of carbon dioxide would be formed? Now this is the kind of question you would want to investigate if you're into greenhouse effect or global warming. You want to know, if I burn methane, which is a common component in natural gas, how much carbon dioxide is going to be generated, because that's going to contribute to global warming. So how do we do that? Well, there's an algorithm to solve most of these. Step number 1 is to convert grams of A to moles of A. And the reason why we're converting to moles is because methane has a different mass than oxygen, and oxygen has a different mass than carbon dioxide. And remember, when it comes down to a chemical reaction, it's 1 atom or 1 molecule reacting with another one. So we need to go from mass to number of molecules. Now we could go to actual number of molecules, but we've talked about already that a mole is what chemists use to handle large values such as Avogadro's number. So we're going to convert the mass of the methane to moles of methane. Step number 2, the most crucial step, and mostly the most missed step, is where we convert from moles of what we have, in this case methane, to moles of what we're trying to find out how much will be formed or how much we need, which is carbon dioxide, which I'll just call moles of B here. And then step number 3 is where we convert from moles of carbon dioxide to grams of carbon dioxide if it is asked for. In this particular problem, it is. So those are the 3 steps to do any stoichiometry problem, do you do all three? Well, it depends on what your starting material is. We are starting with grams here. We are ending with grams of another substance here. So yes, we're going to do all three steps for this particular problem. But had we start off with 4 moles of methane and we'd like to know how many moles of carbon dioxide would be formed, we would have only had to do step number 2. Okay, so how do we do this problem? Well, we write down what's given, 10 grams of methane. We need to convert the grams of methane to moles of methane. All right. In order to do that, we need to find out what the molar mass of methane is. So we know that 1 mole of methane equals, well, we have to figure out how much 1 mole of carbon weighs, which is 12.01 grams per mole, and there's 1 of them. And then we have 4 moles of carbon, and each mole, we got 4 moles of hydrogen, and each mole of hydrogen weighs 1.01 grams, so that would be 4.04. 4 times 1.01 is 4.04. So if we add that all together, we have 16.05 grams of methane in 1 mole. So we use this equality to make this conversion factor. 16.05 grams of methane equals 1 mole. And we make that conversion factor. Step number 2, the most misstepped on a stoichiometry problem, always comes back to the balanced chemical equation. You cannot do a stoichiometry problem without a balanced chemical equation. The balanced chemical equation relates one substance to another. So from our balanced chemical equation, we can see for every 1 mole of methane consumed, we get 1 mole of carbon dioxide. There's no number here, there's no number here. It's understood to be 1 since it's in the chemical equation. So it's a 1-to-1 relationship. A lot of times that's not the case, but for this one it is, and that makes it a little easier for the calculation. Last step, step number 3 here, convert moles of B to grams of B. We need to know how much does 1 mole of carbon dioxide weigh. 1 mole of carbon dioxide, we got 1 mole of carbon, which is 12 grams per mole, and we've got 2 moles of oxygen, which is 16 grams per mole. If we add those together, we get 44.0 grams per 1 mole. All right, so each one of these steps is a conversion. Here's our first conversion factor, here's our second conversion factor, and here's our third conversion factor. So on your calculator, you're going to take 10 divided by the molar mass of methane, 16.05. You're going to then multiply by 1 over 1, which is 1, and then multiply by 44.0 grams. That's the mass of 1 mole of carbon dioxide, and hit equals, and we get 27.4. 27.4 grams of carbon dioxide. Or you could do this, if we only have one significant figure in this number, this would round up to 30 grams of carbon dioxide. All right. I hope this helps. This is a great example of stoichiometry. It has all the major components of it. And if you need more help with these, please email me.